Welcome back to this tutorial series, and in today's video we're going to be combining our Newton's method with our previously defined calculator. In a previous series, if you're new to this channel, we created a recursive descent parser to parse input and functions, and it is an extremely useful tool, and we're going to now combine it with our Newton's method. So to begin with, we are going to define a brand new method. I'm going to simply copy and paste this, and we're going to denote the difference between the native Newton's method and the calculator one by adding calculator. So Newton calculator. And we're going to have different inputs. So before we begin, I'm going to adjust our max iter to be now a function constant. This is because in Newton's method, it should only take a couple iterations to actually find the root. So if your function reaches anywhere near 100 maximum iterations, there's something wrong with the initial value. So now what we're going to do is we're going to adjust these parameters. We're going to pass in our parser, our tokens for our function, pass in a parser for our derivative, and the tokens for our derivative, and then our initial value, and then our tolerance. And I'm going to get rid of these printout statements for now, just so we can get rid of some clustering and some things. Actually leave those two there. So now what I'm going to do is we're going to transform this into our calculator. So we're going to say if our iterations is equal to 0, pass for right now, else pass. So first off, what we need to do is we need to decompose this evaluation into two separate parts. So to begin with, we need to actually add the variable to our parser, x sub n. Now if I was to go here to, let's say, our bisection method, here we have our calculator for the bisection method. Outside of our while loop, we're actually computing values, and we're adding this variable. Well, in Newton's method, we're not computing any values outside the while loop, so we need a way to have our first iteration where we need to actually add our variable. So we say add variable x, add our x sub n. If this is not our first iteration, then we're simply going to place our variable. And then what we're going to do is we're going to decompose this function right here outside. We're going to say f of x sub n is equal to our parser dot parse x sub n. Excuse me, this needs to be our tokens. We're going to parse the tokens of our original function. So now, since these have sort of a common left brace, we're going to extract that out from our loop and then simply have our if-else based on this last part. So now what we're going to do is we're going to say if our parameter derivative is none, then what we need to do is we need to decompose this. We're going to do it as such. So if our parameter derivative is none, that means we don't know the derivative, and also we're going to use the derivative calculator. And the derivative calculator accepts a parser, tokens, and an x value. Before we do that, we need to actually import it from here. So we're going to say derivative and derivative calculator, and import bisection and bisection calculator. So we're going to go back here. Our x sub n, 1, is equal to x sub n minus f of x sub n. Before we do that, we need to actually remove our variable from our parser, and I'll explain why. And we're going to divide by the calculator of our parser, our tokens, and our x sub n. And we're going to add this back. So The derivative approximator requires the same parser as our original function. And the problem is, either way, we're adding the variable x to our parser. So if we were to simply call our calculator here and pass it on, we're adding another variable x. And so we're going to have two variable x's inside of our variable dictionary. And this is going to cause a big problem. So what we need to do is we need to remove the one being added here. This way, we add the new x here, and then we remove it, and then here we add it back. So this is why we remove the current x. This one adds its own x variable, and then we add it back. So now what we do here is we adjust this to say f of xn actually we delete this, we already have this right here. So f of xn divided by the estimated derivative. Now if the parameter derivative, parser deriv. Now if it is not none, that means we actually know the derivative. So what we need to do, I'm going to say parser derivative dot add variable x. I'm going to pass in x of n. F prime is now equal to our parser derivative dot parse our tokens from the derivative. Our x of n 1 is now equal to x of n minus f of xn divided by f prime. And now what we're going to do is we're going to delete this variable. The reason why is simply because we would have to have the same logic here. We would have to say if the iteration is 0, add it, else replace it. And you can equivalently do that, but instead of doing that, because simply the replace variable, if we go back here to our parser class, it removes the variable and then it adds it. So instead of simply calling remove add again and the replace, we're simply just going to remove it and then add it by itself. So everything else stays the same, as we can see here. Now calling this function is going to be the tricky part, because we're going to have to loop over multiple things. And also take note that we're going to implement the bisection method as well. So first off, we're going to say my parser is equal to parser. This is going to be the parser for our main function. And we're going to have our while statement, while true, to get our standard input. Standard in is equal to input of enter function. We're going to say if standard in equals q, or standard in equals quit, then we break. Else, we're going to now get the tokens from our scanner. We're going to break down our input into tokens, and then we're going to get our derivative. We're going to say enter derivative. If not known, enter none. Now we're going to get our tolerance. And then, since I said before, instead of getting an initial guess, we're actually going to implement the bisection method. So we're going to get our A input from the interval. Remember that the bisection method requires an interval A to B, where f of A times f of B is negative. So now what we're going to say is we actually need to go back up here. So if we go to root finding in our calculator right here, so if our f of A times f of B is 0, instead of returning 1, we're going to return none. And now what we're going to do, we're going to adjust this as such as well up here. So we go back, and now what we're going to say is, so if we have an error in our bisection method, that way, instead of returning -1, well, -1 could also be a root value as well. So we're going to return none, that way we break out of the loop. So we're going to say if our derivative equals none. Now, if it does, then we need to use our derivative calculator here. So we're going to say root is equal to Newton calculator. We're going to pass in our parser, my parser, our tokens, and then we're going to simply pass in none for both the derivative parameters. And then for the initial guess, we're going to pass in our bisection calculator, have our parser again, our tokens, our A and a B, and then our tolerance. And then to finish off, we also need a tolerance as well here. But instead of, since we're using the bisection method to just simply get an estimated initial value, we're going to adjust this to some constant, 1e to the negative 4. So we're going to find the supposed root, we're going to find the initial root to the tolerance of 1e to the negative 4, and then we're going to feed that into our Newton's method. What I'm actually going to do is I'm going to extract this, and we're going to say init is equal to this value. I'm going to say if init equals is none, then we break. Else, we're going to pass in our init value. Like I said before, if our interval is not appropriate for the bisection method, instead of feeding in a false initial value, we're just going to break out. Now let's say we do know the derivative, so we need to make our parser for that. Then we need to scan this. And then now we need to do the same thing here. Except instead of passing in none, I'm going to pass in our parser and pass in our tokens. And then at the very end, I'm going to say print estimated root plus the string of root, and then we're going to actually remove, we're actually going to add this root as the variable x. So our function should be in terms of x as variables, and we're going to get our estimated root, and we're going to add this to this variable x with the value root to our parser, and then we're going to parse this to see actually at what value this is in our function. My parser dot parse of our tokens. Oops, I mean to pull that up. And then we're going to simply remove this variable. Alright, so now let's actually run this. Oops, wrong file. Parser is not defined, so I forgot to actually import. I'm going to say from parser import parser, from scanner import scanner. So now we can run this. We can enter in a function. Let's say x squared minus 4. Tokens is not defined. Scanner, we're passing in standard input, not tokens. So unfortunately, this is all the time we have left for today, but in the next video, I'm actually going to go over some examples. So stay tuned.